Hello, this is part 3 of vibrational spectroscopy, and we're just looking at the applications of IR and Raman. So one of the uses is for the identification of ligands, such as linkage isomers. So here is the synthesis, for example, of a cobalt solution, and you can have two different outputs from this synthesis depending on how you make it. So if you let it stand, what you get is this red compound. If you heat it with concentrated acid, you get a yellow compound. So it doesn't really matter what the compound is or anything. What's important is you have cobalt here in the middle, and this one is directly attached to oxygen and then to nitrogen and oxygen. Whereas the yellow compound, the cobalt, is attached to the nitrogen and then has two oxygens. So these are called linkage isomers. And the other application we look at is the use of Raman to quantify pollutants. So just in the infrared example, some ligands have more than one donor atom, each of which can bond to the metal. Often the donor atoms are too close to each other for simultaneous coordination through both atoms. So these are known as linkage isomers. So I've shown you them on the previous slide. So the linkage isomers of this cobalt can be the nitro or the nitrito. So the isomers formed by the ligands which have more than one donor atom but which cannot bond through both atoms simultaneously. So the nitro and the nitrito complexes. And can we identify these using infrared? Okay, so let's look at the nitro. This shows two bands assigned to symmetric and asymmetric stretching. So VS stands for symmetric stretching, and this is the wave number region that we see. So it's the pull from the two oxygen atoms, which is very symmetrical, away from this nitrogen here. And that would be between 1470 and 1370 wave numbers. The asymmetric stretch, so it's one oxygen pulling down and the other one pulling up. This one would be seen as 1340 to 1320 wave numbers. So those two are characteristic of the nitro isomer. Now for the nitrito isomer, what we would see is that, remember, you have the metal, which is cobalt, bonded straight to the oxygen this time, then the nitrogen, and then the oxygen. So if we're looking at the nitrogen with a double bond O, that would appear at 1468 wave numbers. If we're looking at the nitrogen with the single bond O, this one here, then that would appear at 1065 wave numbers. So therefore this band here could be used to distinguish between those two isomers. Okay, if we wanted to do quantitative IR is an absorption process, therefore we can use the Beer-Lambert law, which you're familiar with already. A is equal to ECL. But L is difficult to reproduce and measure in the infrared spectroscopy. You can also do Raman spectroscopy for quantitation. It's not very common, but it is possible. And this is a formula you can use. You don't have to remember it, it's just for reference. The important thing to note in Raman spectroscopy is that we measure the intensity. So this is on our y-axis, and it's wave numbers on the x-axis, the same as in infrared. So usually this is run with an internal standard. So generally a constant amount of internal standard is added to a set of standards for the sample under investigation. The intensity of the band is measured relative to the intensity of an internal standard. So it's called I relative, and how you calculate that is your sample intensity divided by the internal standard intensity. And then what you do is you plot this I relative versus the concentration of your sample standards on the x-axis. So here's a question. If we want to determine the amount of phenol in a sample, a series of standards of phenol containing 0.5% acetonitrile as an internal standard were prepared in an aqueous solution. The intensity of the Raman band of the phenol at 998 wave numbers was measured relative to the acetonitrile band, which was at a different wave number of 918 wave numbers. So this band is due to the internal standard, which is acetonitrile. This band is due to the phenol, which is what we're testing for, that's the pollutant. A sample containing an unknown concentration of phenol was treated in the same manner, and the following results were obtained. So here's my standards in parts per million of phenol. So you see I have 50, 100, 150, 200, 250 ppm, and then your unknown sample. I've measured all of those for phenol content on the Raman spectrometer at 998 wave numbers, and this is the intensity it gave me. So again, you can see this is increasing as we increase in concentration. And then we have the acetonitrile, which doesn't increase because it's the exact same amount that's added to everything. It's the internal standard. So the 918 wave numbers is acetonitrile, which is the internal standard. So then what we do is we plot the graph. So to plot the graph, we have to divide our standard by our internal standard. And we do this for each one, and we get the following table. So here's intensity of 998 divided by intensity of 918. So you see for 50 ppm now, we have this IREL, or relative intensity, of 18.13, and so on. And we do the exact same for the sample, and we get 65.4. Now, just looking at the table before we do our plot of our results, we can see that 65.4 is in between here, which is between 150 to 200 parts per million. So our answer should fall between these two. So then we're going to do a graph, and you see we have relative intensity on the y-axis, and we have concentration in parts per million on the x-axis. And here's my equation of the line, and I have a nice linear response here for my 5 standards. So you just pop your x is your unknown sample into this into the y value actually. So what value is that? Let's go back. Yeah, y is 65.4. So you put 65.4 here into the equation of the line and solve for x. And x turns out to be 180. Or what you could do is read it off the graph. So you get 65.4 here. You go across and down. And I'll just show you there, 65.4. So that's on your y-axis. You go across and then you go down, and it's around 180 parts per million is what you should see. And they're just some examples of applications of infrared and Raman spectroscopy. So what we've done is we've looked at the uses of vibrational spectroscopy, such as IR and Raman, for quantitative and qualitative analysis. So qualitative analysis was the one that we used for the identification of the ligands, where we could distinguish between the 2 different linkage isomers of the cobalt complexes. So hopefully you could see that that would apply for many different samples that have isomers. And then quantitative analysis. So again, we're looking at absorption and transmission in the IR. So again, the Beer-Lambert law would apply. or we can do Raman analysis using an internal standard method.